All right. So I'm getting a little bit ahead of myself here. This is next week's lecture, but this is the only lecture next week, and this is the completion of Unit 5. And so this is a relatively short lecture, and what I'm going to do is I'm going to augment it with some code demos as well, and hopefully that's going to help you kind of see how to do some of this stuff in practice, and also you can watch me bumble through my own way of doing this stuff, which, as you know, is always a fun experience for both me and you. And mostly you. So let's get into it. We're going to now talk a little bit about sort of staying in bounds and separation, and also finding kind of like your future position based on that. We've already been talking about forces, right, like gravity, etc., the attractive forces of the thing you seek, and also the repulsory forces of the things that you maybe don't want. And so combining all of that plus with the boundary conditions of some kind. How do we do this? And so kind of let's take a quick look. So first of all, let's talk about staying in bounds. And you guys have already played with this a little bit in terms of wrapping across the bounds of the orthographic projection. However, you may now be talking about 3D, and that's actually why the orthographic projection idea works really well, because an orthographic projection is actually volume in 3D space. So all we were doing was we were trying to figure out where we are based on that, space. And then with bounds checking, we basically said, okay, if we go more to the right than we want to, then we're going to pop up on the other side and vice versa. And so that's the idea. Another thing we can do is we can create a hard block, right? We can create a wall. We did that in one of the previous lectures, where if your ship or the objects went beyond a particular bounds, they would get stuck there and not allowed to continue. Or we can create other systems where we say, okay, well, once we're outside of a particular set of boundaries, we want to create a very serious force trying to get us back into that boundary. And that'll create a little bit more of a organic type of boundary management than creating like a hard wall or some hard rules that don't look physically accurate. So how do we know whether or not we want to stay in bounds? Well, if we're inside of a particular boundary, we can define a boundary, say, with a square or a rectangle or a sphere or a circle, right? All of these have basically the same measure, right? If it's a sphere or a circle, you have a radius, so you have a point, that's the center, and then a radius, which creates effectively a half vector, in every direction. With a square, you have a center and, say, a width or a height, whichever one you want, and that again creates this sort of half vector. With a rectangle, you have a center point and a width and a height. And all these things in 3D, right? The radius of a sphere applies in 3D. A cube still is just a width or a height, or just one dimension, and a rectangle in 3D is 3 dimensions: height, width, and length, right? So the easiest way to kind of staying inside of our boundary is if we go out of the boundaries, then we try to get our agent to kind of go back and turn around and go in the direction of our boundary. And that's really it. Like, there's nothing too much more complicated than this, right? Like in the previous examples, we've done things like when you hit the boundary, you stop, right? You lose all your momentum, you lose all your acceleration, velocity goes to 0, kind of thing. That works. You'll never go outside of the boundary. This system allows you to create these arbitrary bounds where once you kind of exit, you try to get back in. And this obviously has the consequence of that's not always going to work. Say we're going really quickly at the boundary, there's a lot of momentum, and then we try to turn around, but no matter what we do, we can't get going back in the right direction fast enough before, say, we like fall off the planet or some other bad thing happens. But that's sort of good, right? Like we do want these sort of unanticipated scenarios to arise. We don't want things to be perfect all the time. So that's actually kind of the behavior that we do want to see. Separation. So this is something we actually did in a previous lecture, right? Where if you can kind of create out of a very simple set of behaviors, very interesting emergent properties such as maintaining a minimum separation between myself and my neighbors, and trying to ensure that that happens. There's actually a really elegant algorithm called the Voronoi, I forget the name of it, but Voronoi like boundary or something, which allows you to calculate, these regions and how to ensure, given a particularly arbitrary number of objects, what the separation between them should be, such that they are equally or but most optimally separated. It's actually kind of funny if this has been done for people in an elevator, where if you take a top-down view and you look at people in an elevator, they'll always sort of create these Voronoi patterns of separation. But in our case, we're not going to do Voronoi. We're going to do very simple stuff. We're just going to say, okay, if I'm closer to the person next to me, I want to increase. I don't want to be any closer than, say, a certain distance. And if I am, I'm going to avoid them and apply a force in an opposite direction. So if we're too close, we need to change our desired velocity to steer away from our neighbors, right? We need to kind of turn around and point and start to go in a different direction. And so, right, if we go too quickly, we're going to hit someone, so we kind of have to take into consideration. And so what we want to do is we want to change our direction and steer away from the neighbors. So one way to do this is we can only avoid one at a time. So we find the neighbor closest to us, and if it's too close, then we try to steer away. It's nice because it's easier to program, and it looks okay when there's not that much traffic, right? So if we're guaranteed to only be close to one or two objects, this will work fine, and you won't really notice a difference. But the downside is if you have a lot of traffic, right, the closest one may not be the optimal one to steer away from. Say we're completely surrounded, and the best option is actually to keep going in the same direction. We're going to veer off in an arbitrary direction and hit the other objects. So that's sort of the kind of trade-off here. The alternative is we sort of find the closest neighbors given a particular boundary test. So imagine we take ourselves and we have our center point, and we draw a circle around us, and all the objects that are in that circle we take into consideration with regards to kind of trying to avoid. We can kind of weight the applicability of that force based on how close they are to us. So for example, if we're completely surrounded by objects, the ideal direction is to go straight, to not change at all. And so if every single one of those objects are about the same distance from us, then all of their forces will kind of cancel out. But the downside to this is that it's a little bit harder to code. You have to iterate through all the objects, and you have to sort of apply this test to only a certain subset of them, meaning some testing and logic to figure out what makes sense and what doesn't. And then the third version is actually kind of what I was saying before. It's the same idea before, but we apply a inverse proportionality to distance. So the closer an object is to us, the more we apply that weight. Yeah, cool. So that's kind of it for that. Now the next thing we're going to talk about is finding our future position for pursuit and evasion. So we've talked a little bit about this in the past, but we'll talk about it a little bit more detailed now. So we should have different functions for pursue and evade. And the difference between seek and pursue and evade and pursue and flee and evade we've talked about, which is when we're trying to pursue something, we want to go to where it's going, not to where it is. So we have to compensate for its velocity, predict its future position, and then go in that direction. Similarly, evading, we're not fleeing the position of the object, we're fleeing where it's going. So it's kind of like the difference between pursue and evade from flee and seek is a certain intentionality. You're kind of thinking about where this object will be and then using that position to make decisions. And And then we'll talk a lot about, there's other steering behaviors as well. We talked about staying in bounds already, but avoiding obstacles, we haven't talked about that too much yet, but we will. So seek and pursue we already have. So now this is something that we've talked a little bit about. If you were an agent in one of these environments, right, you would not necessarily be able to see everything, right? You would be looking from their perspective. But us, as the developers, we sit on top. We're at the game engine level, and we can see everything that they can see, everything in the environment entirely, right? So we can basically say, okay, position and velocity of this object, and go through all the objects, even if in theory we can't actually see these things. Reality is a little bit different, right? A flock of birds, a particular bird can't see two birds over because of occlusion, right? When we're walking down the hallway, we don't know what's on the other side of a corner, so we may be walking and bump straight into somebody that's going in the exact opposite direction than us because we didn't see what was around the corner. So you have to kind of set limitations to your agents in games, otherwise they behave in unnatural ways. So it goes as far as legitimately training agents using computer vision to look and to render and to make things go pretty deep. But more simply, we can just sort of create rules of, for example, the corner test, right? I can create a test to say, okay, I can't see beyond this particular boundary, so I'm only going to consider objects that are visible to me or objects that are in front of me. Like, you can do very basic tests, logic, to determine what things we can consider in our data set for making decisions against. Because once we have the data, right, once we have the position of an object to avoid and its velocity, great. But how do we get to that position and velocity? Those are the things that you kind of have to realize. Well, our game is going to have perfect information, but perfect information sometimes makes for a very bad experience. Like, for example, imagine Pong. I brought this example before. A game of Pong where the paddle of the computer player can just set its position to the Y position of the ball is a game of Pong you will never win, right? So ultimately, you want to add some logic there. For example, give it a maximum speed to slow it down, right? Or perhaps instead of using the Y position of the ball, it tries to do some kind of calculation that's error prone, like rendering its view and then making assumptions that, oh, the ball is here, right? So for example, you can do some fun tricks where if you set your position to the position of the ball, maybe you can trick it, right? So games ultimately, or interactive experiences, are really about creating fun experiences or interesting experiences or realistic experiences, not necessarily creating perfect ones, which is a hard thing to balance. So in this case, we'll talk a little bit about what we want to do. Here, we talked a little bit about this already when we introduced autonomous behaviors, but to recap, right, if I want to pursue the green agent, the blue agent wants to pursue the green agent, and I know the green agent's velocity and current position, I know that the green's future position is a particular point, and then I'm going to go to that. Right, there's the whole famous Wayne Gretzky quote, right? Pass the puck to where the player is going. And this is sort of what you're doing here. You're accommodating for their motion, because if you're going to go to where green is at this very moment, you'll never actually get to them, right? You'll always just be a little bit behind if they're moving. So now this is obviously it was an adaptation from a in-class type of class, like so this was take a moment now to kind of sit back and brainstorm and think about how you would find the future position of any agent, and where will the agent be after 1 second, 2 seconds, 3 seconds. Like, how do you predict its motion given kind of instantaneous information? So right now we know its position and its velocity, but we don't know what that will be in, say, 10 seconds from now. So how can you predict the position of a different agent given incomplete information, right? Also, and feel free to pause the video to do this. Also, another thing to kind of brainstorm is imagine a velocity. Like, imagine you're not given the velocity, you're only given the position, right? How would you then predict the future position of another agent if you're not allowed to have its velocity? That you're only allowed to have its to measure or to observe its position, right? Um, so I'll let you think about that for a minute. All right, let me jump in a little bit into Unity. So I set up a new little project here, and all I've done so far is I've added my behavior script that is here. This is our script from before. This is like the vehicle script. I'm going to be kind of changing it up and refactoring it so that I can use it to, inherit, so things can inherit from it a little bit. First thing I'm going to do, I'm going to create a empty object, which will be my manager, and I'm going to create in my manager a script, which is manager script. Cool. I'm going to put that into the scripts folder, and let's pop open our manager script. Great. Next thing, let's create a plane. Great. And let's make it a little bit bigger. Cool. And now let's move this here. And if we play, nothing happens so far. Great. And another thing I want to do is I want to create a prefab folder. And in the prefab folder, I'm going to create a new prefab. If I can find it. No. I can't create a... Not sure why I can create a sprite but not a prefab. Maybe I'm just not seeing it. Whatever, I'll create it here. Okay, so let's create a cube, and let's position the cube at the correct position, which is 0.5. Okay, great, and we're going to rename this as a zombie. We're going to make another one human, and then we're going to add a sphere. I'm going to rename this orb. Great, and we're going to pop all of these into the prefabs. I'm going to delete these here, and then I'm going to make this guy right. I'm going to change select material. No. I'm going to pause this and do a little bit of flesh work here, just really quickly. Okay, so now I've added a little bit of materials to my scene. The next thing I'm going to do now is I'm going to create use the manager to instantiate these objects. So let's go into the manager, and what we're going to do is we're going to set up our scene. And the first thing I'm going to do is game object. We're going to do this all privately. This is probably not what you want to do for your project, but it's up to you. So we're going to create our orb. And so what we're going to do that is morb is going to be equal to game object resources dot load prefabs it's just prefab orb, and let's see if that works. Did it work? Hold on, let me debug this a bit. Okay, and I'm back after some Unity trivia. So to use this function here, instantiate using game load. I'm not actually sure if this will work without the instantiate, but probably not. It'll probably just load up my object. But to get this line of code to work, you need to create a resources folder inside of Unity, which will allow you to load from that resource without having to instantiate the object ahead of time. I don't believe it'll instantiate the object, however. So, okay, sorry about that. Anyways, so now I'm going to instantiate this this new orb. I'm going to set its height at 0.5, and there we go. We'll actually see, and now we've got an orb set in position 0. Another thing I'm going to do is I'm going to make this play area much larger. Great. So that's going to be our orb. The other thing I'm going to do is in our prefab, I'm going to create a new script called orb. Great. And where is it? Okay, great. That's going to go into our scripts folder. And one of the other things that we're going to do here is an orb. We're going to, my function for the vehicle is actually called behave. So I'm going to have it inherit behave. And keep in mind, behave has all this stuff that we're going to get rid of. But for the time being, let's see what happens when we launch this thing. And now our orb, and it has a, where's our script? And you can see it's seeking nothing, which is cool, but we can, it's not going to do too much. Another thing we're going to do here, let's position our camera. Not that it really matters, because we're probably going to be doing most of our work here, but that's fine. So great. So now what I want to do with orb, so I'm going to take this code actually out of the manager, and I'm going to do this orb game object and also keep in mind that our behave has a position, right? And so, and we're not going to update, we're not going to use this. We're going to actually have our update called here. So this way we can, in orb, set our point position is going to be, our orb is going to be private float radius is going to be 1.0, and so we're going to create a position new vector 3, 0.0, radius divided by 2.0, 0.0. Great, and that should hopefully and also we need to fix this. So notice that it's private. When you do into class inheritance, you have to understand that private is something only that class can have access to. Public is anything can have access to it. And then protected allows us to sort of, anything that inherits from that class is a friend class, can also have access to it. So now by making this protected, the orb is able to set our position. And let's change the name of this to m_point_position, which indicates that it's a member. So now with a bit of luck, the orb will no longer be in the middle of the will no longer be in the middle. Apparently not. Let me figure something out really quick. Yes, of course I'm doing this wrong. So now that we have the orb code here, what we need to do is we need to create a new orb object. And here we go morb equals new orb. And that's it. And now, now when we launch and we start the application, we'll create an orb. Maybe not. One moment. All right, we're back. So I did a bit of juggling. Let me kind of walk you through what I landed on. So the manager ultimately still instantiates this game object orb. Keep in mind that in the editor, the actual prefab, right, has this script attached to it. So the start code of orb will get hit. And so I added one more thing that needs to be sort of noted. I added the call to start to the behave upper level object, which is here. And this will sort of set our world screen height and world screen width to the camera size. Now we don't really want that yet, I guess. We kind of have to be careful here. So we're probably going to get rid of that. But you can see that already the position of the that we're going to start to kind of flesh this out. And so first we want to have our endpoint position. We want to have it some random value. We'll deal with this world screen width stuff in a little bit. Let's just call this 10 for now. We don't actually want that in the Y, we want this in the Z. And then we want our radius divided by 2.0. Oops. Not here. We want to be in orb. Right. So that will hopefully start to get us some random positioning, but it'll probably not work yet. So let's see what happens. The object is now positioned slightly randomly, as you can see, around the window. The other thing we want to do is we want to, let's call this ground, and let's use this as for our manager, the ground. So let's add a new game object, private game object ground, public I mean. And now in our manager, let's take the ground to be here we want to set the ground to there. And now what we can do is we can create a float ground width, ground height, right? And if our m ground is not equal to null, we can then do m ground bounds, or get component collider, which I believe we already have a collider. One second, I always forget how to do this. Alright, so making progress here. Ground width, ground height is going to be equal to this mesh filter. Notice that the mesh filter comes from here, so the mesh collider for this. There's another way to do this, I think. I'm not sure if mesh filter will work unless... maybe this will work without having the mesh filter. Yeah, I guess so. So I don't need to do that. And this will give us our bounds, similar to like in Unity 2D when we did the sprite boundary checking and that kind of thing. Let me just make sure that this code is working, because I don't trust it. I want to see that I'm getting something like 10 or some value similar to that. Let's attach to Unity. Manager. I'm not sure why. Alright, whatever. I'm not entirely certain why, but now, now that we have our ground width, let's create some new functions. morb set ground width, ground height, and let's put this in behave, actually. Public void and what we're going to do is we're going to create a public float m ground width, m ground height 0, and now we're just going to basically pass this. Cool. And then we're going to use that in the orb random position calculation. And one last thing, the ground height is incorrect. It's going to be, we want our z value here. And set ground. One moment. Alright, cool. I learned some things. So, just to go through this, I had a little bit of stuff here. So first of all, this works. You do need the mesh filter. Sorry for all the detail, but you guys might hit this stuff too, so it might be helpful. And then also, I'm loading the game object, the orb game object here, and then I'm calling set ground on it, which is important, because what this will do is it will then go up to the behave script and set this ground width and ground height. And so then when you instantiate the object, it will have that same ground height and ground width. And I've also fixed a little bit of the code. The random was being generated in a funny way. So now when I go back here and I hit play, you'll notice that the orb will show up in kind of random places, scaled by the size of our thing. It should be. There we go. It's very similar places right now, but that's okay. Okay, cool. So let's do the same thing for our humans, and let's put them into an array or a vector or something. Okay, sorry about that. So let's create now a private vector. No. 1 second. Okay, sorry. I always get a bit mixed up with a few things with C# versus C++, which is my preferred. So let's make a list of zombies. Great. And now we're going to create, let's maybe make 10 zombies. First, let's load our game object zombie. And let's set the ground as we did for that. And now let's create a game object 10 zombie to instantiate the game object. Actually don't need that bit, do we? Because we're going to set that automatically anyways. And then we're going to end zombies, add our temp zombie. And again, repeat this for the human game object. I believe human's the name of our thing. Yes. Human, and then temp human and temp human, and then to our humans. Another thing that I nearly screwed up here is that. In fact, we might want to have different number of humans. For now, let's actually only make 2 zombies, or let's just test it to make sure that all of this is working. And all right. So let's just see that it works, because we expect 10 objects and we only see 1, and there's a lot of errors. Well, that's why. So cool. So let's fix this really quickly. You'll notice there's an issue here. Orb, this should be zombie, and this should be human. And here we should create a couple of new objects. Great. C# mono behavior script, we want zombie, and we want human. You'll notice that when I do that in the editor in the Visual Studio, it'll also show up in my scripts code here. And then I can, I don't want to create a new script actually. I want to apply my human script to my prefab. How do I do that? There we go. And now I can add my human. Okay. I'm not having very much luck today. Let me do this. This is such a hack, but it'll work. The script class cannot be found. Well, actually, what we want is first orb, or no, behave, and also the human is we want behave. Great. So that should at least help that, and then maybe that'll let me. Great. That's annoying. It really should just let me do it, but that's fine. Okay, put these back. It's a funny way to get work done. And at least now we should be able to, so as you can see here, we probably want to reproduce the zombie code. And we'll have to float height equals 1.0. Similarly, human there we go. You can see that like over time you can make this more and more programmatic, right? It doesn't all have to be, there's a lot that you can do to make these values come straight out of your game. You don't have to hard code them like I'm doing necessarily. So let's just see, will our stuff show up? Cool, well we got, looks like one zombie. That's it. So at least something worked. So let's see what else. What's the issue here? So we had some kind of error. Let's see, let's clear this and see what happens. Okay, something went wrong. Let me pause while I figure this out. Alright, the issue was apparently that the prefab didn't actually have the script attached for some strange reason. So let's see, let's make sure everything works correctly. So now I've got one zombie. I'm still blowing up here. Alright, let's see. I'll be right back again. Okay, as usual, it was a very silly issue. The list was never getting initialized, so it was just an empty reference. And as a result, no objects were actually getting added, which sucked, but it works now. So let me human game object. And so what will happen now is you'll notice when I hit play, here are a lot of objects, but you'll notice that they're all in the ground, but there are 10 of each. 1, 2, 3, 4, 5, 6, 7, 8, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. So now we got to figure out why the zombie behavior is not actually setting its correct position. Oh, well, another thing we need to fix is the update cannot be called. If we call the update in the child, then the update of behave is not going to get called. So I'll just delete it completely. And now hopefully the new positions of the objects will be present. For whatever reason, it's the 10 that it's being applied to the ground size is not taking into consideration the actual scaling of the object. So let me fix that as well. So in the manager, what we need to do is we need to not just do the bounds, but we also need to multiply it by the, maybe the extents is the correct thing to use. Well, no, this is just half the size of the bounds, so this is just going to give us half the size of that, which is useless. Let's see if there's a... Let's do mesh filter MF is going to be equal to the mesh. Actually, let's just do this. Actually, I don't need to do that. What we can do is the following times m ground transform scale to x. We're just trying to not do this hard-coded, right? And hopefully now everything will be in one direction for some reason. Great. So we'll fix that in a second, but for whatever reason the size z and the local scale z is we're not going in that, we're not applying it correctly, and that doesn't make sense. So why is ground height not getting set correctly? Let's try this, see if there's if there's an issue with the scaling of z. No. I'm getting a little bit of z scaling, but clearly not very much. It's probably some kind of let's see if we switch it to x, because we know x is working. So clearly there's something else in our logic not working, because it's still in a line. So these values are probably okay. I'll be right back again. Alright, so looks like I've figured out most of my issues. Cool. So now when I hit play, I get a random assortment of things. You can see that the sphere is there and so on. Great. I won't go through all the changes that I made to make that the case, but basically now you set the ground after you instantiate the object, and then you create, there's this function called the random position that positions it randomly. I also noticed that constrained position was kind of screwing everything up effectively. And so now we've got all the pieces that we need. And the next thing is we need to be able to set the target object of the objects. So let's just start off with the humans. And with the humans, I'm not going to do the whole assignment, obviously. I'm just kind of giving you the pieces that you might need. And so another thing we want to do now is we want to be able to create a function here, public void set target object. Object target. And now what we're going to do is let's rename this to target object, and we're going to now set target object to target. And now in the manager, what we do, just like we did here, is set target object. There is no corresponding, right, so then we have to set it to the orb. And now, with a bit of luck, we'll see nothing happen. Alright, so let's check out our code and kind of figure out why that may be the case. So we haven't looked at this in a bit. One of the things that we know is, let's actually take a look at one of these human objects when we're running. So let's take a look at a human. We can see here that the speed is 0.1 and the max speed is 2, and we're seeking. If we change it to pursue or seek, nothing happens. If we change this to 2, nothing happens. So let's go back here and see what's going on. In the update call, for each object, well, there's one thing that we maybe want to do. So instead of having a target object, what we're going to do is we're going to change this to a list of game objects and target objects, and then we're going to set that to a new list game object, and then instead of set, we're going to add target object. And then I'm not making this particularly smart, so if you add something that already exists, you're going to add it twice, but this will allow us to add multiple target objects. So now instead of going through each game object in find object of type, we're going to instead go through all of our target objects, and we're going to get rid of this code for now. And then we're going to game object target object is going to be equal to obj. Then we're going to update that, so our direction is going to be target object this way. We're going to get rid of this code for now. This is our kind of like combination code. Then we're going to go through this stuff. Fix some of this here. We're not going to do any evasion stuff yet. And then we're going to get rid of this code, because we're not going to do velocity stuff for this. And again, we're going to remove this for the time being, because this requires pursue and evade require velocity. If we want to add that, we need to add a fair bit of functionality. And then we have to add target object. And now you can see the humans are all coming at the sphere. Great. Now what if we added something very similar? So we have, let's create the zombies second, because we want to go through all the zombies. Actually, it doesn't matter. Let's do this. For each game object human, let's call it obj in zombies, for each zombie, and then for each human object in humans. Let's make this a little bit more for the zombie object. Let's, and then when we do the get component behave, add target object human object. And now look at our code and behave, right? For each one of these, we're kind of like creating a, we're creating this whole, you know, thing. And what we want is we're going to seek out for each object, and we're going to add to that our velocity, the direction and the speed and all that that we need to be going in. And so the zombies will go after the humans as well. You can kind of see the sort of averaging that's happening right now. And so what you want is you do want, you will need to add a lot more kind of thinking, right, than what this very basic behavior script is doing. So to get from this to the assignment, there's a fair bit of work. Eventually they're all going to converge into this one little spot. So one of the things you want to add, right, is making sure that we, well, a very simple thing we can do actually is actually take advantage of the rigid body system, right? If we add a rigid body to all this, and to the orb even, right? Now we'll see a slightly more interesting thing. Not really. That's right. We can't do that. Do not add the rigid body. That's just going to be, because we're doing all of this stuff manually. But to talk about this more eloquently, right now, as the, you know, for multiple objects, if we're seeking, we're going to go through this and we're going to add that direction over and over and over again for the zombie. And so you might not want to do that. You might want to have, for the zombie, a seek where it looks for the closest one and then uses that instead. So if we were to do that instead, we'd get this out of the for loop. And what we'll do is we're going to put our game object, target object's going to be our target object 0, right? And then we're going to have a vector 3 min distance is going to be to m It's basically going to be this. Magnitude. Great. So now this is going to be our minimum distance, and for each object, if I'm doing this super quickly, but if this magnitude is less than min distance, right, then min distance is equal to this, and our target object is equal to obj. And we get rid of this code here. And so what this will do is it will look for the closest object, and that will be it'll iterate through all of the target objects. And so for the humans, there's only one target object that's going to be the orb. But for the zombies, they're going to try to kind of find the closest object to them and go after that one. Which doesn't seem to be entirely true here. It looks like they're all after a very specific one. So something's wrong in our code. So let's go through this code and make sure. Let's find the bug. Let's play find the bug. So great. Right now we are in, okay, min distance, our target object. Yeah, let's run this a few times, because right now it's, our target object is a human clone. One second, let me go through this. As usual, the bug is a simple one. I was not using obj in this for loop. I was actually using the target object. So anyways, fixing that, now you can see that the zombies seek out whichever, human is closest to them. And that's visible now by these zombies following specific humans. And yeah, it's pretty neat. Like, the other thing you can do, for example, if you're doing it this way, you can also add, for example, target. Like, let's change this to. Let's rename this to seek. Oops. Let's rename this to seek objects. Right, and then you can also create a flee objects, and then you add a flee object. Right, and then change this to seek, and in behave, and in manager we add. So the humans seek the orbs, the zombies seek the humans, And then also we also add each human will flee the zombies. The zombie object. And what we do here then in behave is we kind of change the nomenclature a little bit, right? We change the target object to seek object, right? And then we can also do a very similar thing to the flee object. We don't have to flee, and then instead of seek objects we do flee. So this is just finding out what's the closest object that we're trying to get away from. And instead of, and now we have to change the v direction to the seek direction. Oops. Sorry. The seek direction, right, and the seek distance, and the seek direction. Great. And now we can do the same thing for the flee direction. Flee, 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 flee. We no longer really need the object behavior type anymore, so let's just do this. So velocity, this is for seek, right? And then we do the same thing for the velocity for flee. And right, and keep in mind that if and flee objects size or length count. Every language has a different nomenclature, so we just stick this all in there, right? And similarly, if seek objects are greater than 0, should also add this for let's get rid of this for now, although we might want to have this code here just for future. Get rid of this. Great. Do we even need this? No. And so now we've got, if we have objects in the seek count and if we have objects in the seek count, the two will interplay. So for example, zombies don't have anything to flee, so they won't flee anything, but you'll notice now that not only are we trying to get away from the zombies, we're also we're going for the goal, but we're also going to be trying to avoid the zombies, which will create slightly more interesting behavior here at the center. Now you'll notice that it's like, okay, there's still a lot of mess, and everything is we've got sort of XYZ going on here. As you'll notice, there's a lot of issues with the X and Y, which I haven't done much to prevent. What you can do, by the way, if you just zero out the, right, if you just say v velocity dot y is equal to 0, that'll get rid of the z component. The other thing you can do is we can make fleeing like way more important than seeking. So we're going to increase the speed, the maximum speed of fleeing. Well, like, let's do it by 3. And you'll kind of notice the effect of that. So when you're trying to flee, the objects are moving faster. So you'll notice that, especially here in the center now, there's a lot more, reaction. If we increase this even more, say we do set it to 10, and keep in mind we do have a scale, like the way we did this is the amount is proportional to the distance. So the farther away something is, the zombie is, the less the flee force is. If we get rid of that, let's get rid of that. Just for demonstrative purposes. Still not seeing. So I feel like there's a bug. 1 second. Okay, so I got rid of another little thing that was. So we had this here, max f dot max seek distance of 0.5. So this was making us seek like way stronger if we're far away. Now it's creating. So now with 10 in the velocity, the acceleration, the force due to fleeing. And keep in mind, I'm not doing like mass-based calculations. That's something that you guys will have to do in your assignment. But notice with 10, the fleeing is overriding the movement decision. Right, so we're fleeing, and like notice here, for example, this guy is going to come into contact there and make a quick decision. Oh, this zombie is now closer to me, and you can see that in fact seeking has sort of become less important, right? Because fleeing is significantly more important. We also have kind of a max speed, so that's one of the reasons everything's moving kind of slowly. So like if we make our maximum speed 4 or 3, we might start to actually see them getting away and then being able to sort of make their way back. So now you can kind of see how playing with all of these parameters lets you kind of create a pretty dynamic scene. So if we're watching from far away, and the orb is here, you can see these two are running for the orb, but also avoiding the pressure of the zombies. So another thing we can do, so let's put this proportionality back in there, but let's give our humans ungodly speed. You can kind of see they'll make it, but they'll run away, and as they get closer, sometimes that's the problem with this 1 over flee distance. It doesn't have like you almost have to do a math min on it. I don't know. Let's do this. Actually, it's almost like you want to have this. And what this will do, the reason this will work a little bit better is because it's going to amplify the effect pretty significantly when the flee distance is less than 1. So what will happen that's interesting is these are going to converge, but you can see they're really running away. So that's about it for this lecture. I'm sorry for kind of bouncing around and running into a variety of issues, but hopefully this is pretty helpful for you guys to kind of understand how to build the systems that you need to build in the exercises and for for this unit. In one of the past lectures, I talked about how to do pursue and evade, so you'll have to build that capability, and also now that you know how to create the bounds, you should also be able to create an explicit force that forces them back into the play area, so to speak, so that objects can't just go off into space. So pretty fun. Let's see what happens if we do 100. And I'll leave on that. So cool. Whoa. Great. See you guys soon.